No, I've done this before. Oh, hi everyone. Thank you so much for showing up for your math learning. It's Mr. Jennings. And today we are, as promised, this unit provides us a lot of opportunities to review old content. So today we review working with rational functions, and this time in the context of inequalities. So this is some of the most more challenging algebraic and graphing material we've looked at. And the examples in here talk about using algebra to solve them. But I always encourage you to do a problem. If it's an important problem, do it with two different methods and see if the methods agree. And when they agree, you can be very confident that your answer is correct. It'd be very difficult to make like the same different errors using two different methods and get the same result. So it's unlikely that you would agree if you do have an error. So that's some of the benefit. It helps you on the test to check your answers and make sure they're correct. But more importantly, when you're seeing it visually on a graph and you're seeing it algebraically work out with your functions, you're reinforcing your understanding of the mathematics that we're doing by keying into two different modes of approaching the problem. So these are the things that we will do today. Let's just get started. So rational inequalities. We have an inequality that contains rational expressions. So something like a polynomial divided by another polynomial, and we have inequality symbols like greater than, less than, alligator or equal to, alligator or less than. Let's go. So our first example here, we have x minus 1 over x plus 3. So this is what I'd encourage you to do. Suppose that we have this function, f of x is equal to x minus 1 over x plus 3, and then find the key points. We're going to use the key points for both the algebra and the sketch. Let's make both at the same time. How do we find the x-intercept here? How do we do that? Yeah?
When the top is 0.
When the top is 0. So when f of x is equal to 0, x is equal to, x minus 1. Let's really do this step by step. X minus 1 would be equal to 0. And that will give you x is equal to 1. So that gave us this key point 1, 0 is our x-intercept. You set it equal to 0. Good. Now let's find our y-intercept. It might be useful. F at 0 is equal to 0 minus 1 over 0 plus 3. That's a fancy way of saying minus 1/3. So that's going to help us with our sketch, but it's not really a key point for other things. Next, where does this thing have an asymptote? So there's a horizontal asymptote, and that's at y is equal to 1. How did you know that?
The coefficients in front of the
Yeah, as x gets very, very big, as x approaches infinity, it totally overwhelms the minus 1 and the plus 3. So you can see it would be like as x is 1,000,000, you would have 999,999 over 1,000,003. It's very, very close to 1, but just underneath. So if you were to do like as x approaches, y approaches here, you would say as x approaches positive infinity, y would be approaching 1 from the negative side. And as x approaches negative infinity, y would be approaching 1 from the positive side. This is useful for creating a sketch. We're not really going to need that for the problem at hand, but again, review. And do the problem two different ways. It's very useful. Okay, and then what about vertical asymptote? Where do we get one of those?
The denominator is 0.
Yes, so if we have x plus 3 cannot equal 0, then you have x cannot equal minus 3. So there is our vertical asymptote right there, as x is equal to minus 3. And so then we might test that in our table here and just test, well, what if x was 3.1? As x approaches, negative 3 from the negative side, so if x is minus 3.1, we would have a negative divided by a negative there. That's going off to positive infinity. And as x approaches negative 3 from the positive side, like we have negative 2.9, negative 2.9 plus 3 over there, that would be a positive number, but we're dividing a negative number, so it's very, very negative and large, and so this would be negative infinity. So we can do these little tests pretty quickly and then get a good sketch. So our sketch would look like this. We have our asymptote there at -3, our asymptote here at y is equal to 1, and then we have our y-intercept there at -1/3. We're going to come up at the key point 1, 0, and then we go off to negative infinity as we approach -3 from the positive side, and then over here we're approaching infinity, positive infinity from when we're approaching -3 from the negative side. Now, if we're just laying this out algebraically, we just lay this out with our key points, our restriction here, -3, and the spot where we have a 0, 1. And then we're just going to test what happens in between all of those. Let's test f at -9, because that's clearly past -3. And then we get -10 over -6, which is a fancy way of saying 5/3, which is to say a positive number. So in this range, we are positive over here. Between -3 and 1, well, let's check f at 0. We already evaluated that. That's -1/3. -1/3 is to say a negative number, so we are negative in this range in here. And then after 1, let's test a point like f at 11, because that gives us 10 over 14, which is a fancy way of saying 5/7, but that's a positive number. Okay, so that's how I get those. And then I might write it in using interval notation as saying negative infinity to -3 not inclusive. We definitely don't want to include this. There's an L there. So we're non-inclusive because x cannot equal -3. That's an asymptote. We know that from our sketch. We know that from our understanding. X cannot equal -3. But then we also have the union of that and inclusive 1, positive infinity. The reason why we include 1 there is because 1 is absolutely a point on this graph where x is allowed to be, and we were told this function wants to be greater than or equal to 0. And so that's how our solution would look in that case. Questions about this one? Let's go. Next one. Now if we've got this one, oh, this one harder. Okay, so factor. That's our first thing that we're going to do. So let's call it f of x and go ahead and factor it. Show me how fast you can do that. You got it? Oops, that's 2. Okay, so if I call this f of x and I factor the numerator and denominator, who's got the numerator, not Nathan? B.
X minus 3x plus 2.
X, what flavor of 3?
X plus 3x minus 2.
Yeah. There we go. And then the denominator? So I do this in rough work. It's even rough work to my rough work. I'm going to take 2x squared minus 2, multiply those, get -4. I want to multiply to -4 and add to -3. Those numbers are -4 and +1. And then I factor by grouping. So that gives me 2x times x minus 2 plus 1, this should be 1x, times x minus 2. And then that is the same thing as saying 2x plus 1 multiplied by x minus 2. And then we get here, what type of thing happens when we do that? We get a whole. Good. So in this function we have a whole at x equals 2 and y equals what? How do we find the y value of the whole? Gavin?
Plug the x value back in.
Yeah, you plug it into which expression?
Already canceled out factors.
Yeah, plug it into the factored expression, because if you plug it into the one that still has the canceled factor, you're just going to get 0 over 0. So that's right. Yeah, good. So and then when we do that, we get 2 plus 3 on top and 2 times 2 plus 1 on the bottom. That's 5 over 5. That's 1. So we have a whole at 2, 1. Cool. So that's an important point. Let's circle it. We've got, this is roughly the same thing as x plus 3 over 2x plus 1. And that wants to be less than or equal to 0. So where are our key points with that function now? Sorry? Oh, I thought you had something. Okay. So where's this thing's x-intercept? Where's the x-intercept? How do we find an x-intercept? I remembered last slide, but I forgot this slide. Luke?
Setting y equal to 0.
Yeah, we set the value of the function equal to 0, and that is to say set the numerator equal to 0. So that is to say x plus 3 equals 0, or x equals minus 3. So that gives us this key point, minus 3, 0. Cool. And this one's a whole. This one's an x-intercept. Our y-intercept, we just set x equal to 0, and you get 3 over 1. So we also have the point 0, 3. That's our y-intercept. Just looking at that, set x equal to 0. It's useful for our sketch, not useful for the other things we're doing. And then we also have an asymptote. I break a lot of things in here. Okay, let's go. Yeah. So we were looking for the asymptote. What's the vertical asymptote here? Sorry? What did you say? Yeah, negative 1/2. So we have a vertical asymptote when 2x plus 1 equals 0, or in other words, when x equals negative 1/2. So that's very useful. And all of that helps us set up our sketch. We also have a horizontal asymptote at 1/2. So that's 1/2 equals y. So that's useful for the purposes of our sketch. Make a sketch because it helps you organize your thinking. Here's our vertical asymptote at negative 1/2. Here's our horizontal asymptote at positive 1/2. And then we know that the y-intercept is 0, 3. So that's up here. The x-intercept is at minus 3, 0, so that's back here. And this thing is going to have this behavior this way, and that way, and this way. Okay, but it also has a hole, so we should show our hole at 2, 1. So let's just put a hole over there so we remember that it exists. Okay, so now when we're, yeah?
So if it's directly on the line, so if it had, it's not anywhere else on the chart, it's right on the path of the line.
What's that, the hole?
Yeah.
Yeah, the holes are usually going to be like right in the line of the function.
So it just doesn't exist there.
It doesn't exist for that infinitely small value.
Right.
It exists right up to 2.9999997 and right at 3.000001, and it's continuous through there. But at the point 3, it does not exist. Yeah. So if you had an infinitely small foot and you happened to step on that infinitely small point, you'd fall infinitely far down. But it doesn't have like asymptotic weird behavior there. It just like meets but doesn't touch. Yeah. It's like trying to kiss your reflection in the mirror. Yeah, I see some of you know what that's like. Yeah, okay. All right, so let's go. So what does that look like when we do our tests here? Well, we're going to put on our key points. So we have this minus 1/2 here. So we're going to test things around that. We had no x-intercept, but we did have this hole. So we better test around the hole just to be sure. Okay, and we want to know when is this thing less than or equal to 0? Well, oh, sorry, we did have an x-intercept. What am I saying? We don't have an x-intercept. We do. Of course we do. So we're just going to stretch that out a little bit and then put it over here at minus 3. Okay, so let's test f at minus 10. And that will give us minus 13. over minus 19. Minus 13 over minus 19 is positive. Sorry, not minus 13, minus 7 over minus 19. So it's positive. And then in between here, let's test f at minus 2 because that looks easy to test. Minus 2 plus 3 is 1. Minus 2 times 2 is minus 4 plus 1 is 3. So this gave us negative 1/3. And negative 1/3 is indeed negative. What? What? Oh, of course it does. Of course it does. Yes, so that's negative. So that's what we're looking for. And then between minus 1/2 and 2, let's try f at 0. We already have that point. It's 3, so that's positive. And then after the whole, let's test f at 10. That gives us 13 divided by 21. Ooh, Fibonacci. And that's also positive. So we have our range that we're looking for is this one, because that's where it's less than or equal to 0. So we would say our range is minus 3 to minus 1/2, not inclusive. That's how you do it algebraically. Keep going. Whee! This one pretty straightforward too. I see that I can factor that as a difference of squares, as a dots. So that's x minus 3 times x plus 3 on the top, divided by x plus 3 on the bottom. That's all less than 0. This would cancel and give me a whole at minus 3. So we have a whole at minus 3, and then if I input minus 3 there, that's minus 6. And the denominator, well, I have no more denominator. No, I have a denominator, everyone. It's 1. Okay, when all the factors cancel away, that's 1 down there. It's not 0 or something. So that's minus 3 minus 6 is where our whole is at. Cool. If we set this thing equal to 0, then we'd find that x equals 3. Because if I have like x minus 3 as my now function, and if I set that equal to 0, then x equals 3. Okay, so there's one of my key points there. I don't have any asymptotes. This is just a linear function with a hole in it. That's all it is. So a sketch would look like the line x minus 3, so it starts down there and goes up. This is the point 3, 0. And then down here, there's going to be a little hole right there at minus 3. Minus 3, minus 6. So that's what our sketch would look like. Our interval table can look like we have minus 3 down here, 3 over here, and we're going to check here f at minus 10. Minus 10 minus 3 is minus 13. That's negative. After the whole, we'll test f at 0. That's minus 3, and that's negative. And then past 3, let's test f at 10. Last time I checked, 10 minus 3 was 7, and 7 is a positive number, so there you go. So we have this one is 3. Oh, wait, where's this less than 0? Oh my goodness, that's a much better question. Okay, where's this less than 0? Well, visually I can see that anything from here back that way is going to work except for this precise value. So I need to do this in 2 little intervals. So I would say negative infinity to minus 3. And the union of that with minus 3 and 3, but this one is inclusive. Okay, I need to include this value because that's actually a valid value for this function. All right, so that's what an answer would look like there. Let's take some time to write what it would look like using inequality notation. So I would say x is less than minus 3, or minus 3 is less than x, and x is less than or equal to 3. That's what it would look like in interval notation. Let's keep going. Oh, wait, this one's not equal to 0. You suppose we should multiply both sides by t minus 4 to get everything up onto the same line? Hey, Gavin, do you think it's a good idea to multiply both sides here by t minus 4? Yeah, it looks solid, right? Because we're allowed to multiply by things so long as they're not equal to 0, right? Wait a minute, why hasn't Mr. Jennings done it yet? What would be the problem with multiplying by t minus 4? Yeah. Do we have to, is that what you were going to say? Do we have to flip our alligator?
Well, you wouldn't know because you don't know what t is.
We would have, do you mind getting the door? Yeah, just pull it close. Thank you. We don't know yet, is t minus 4 positive or negative? Well, we do know that it's negative for some values of t and positive for other values of t. So we would have to divide into cases if we did that. Do you feel like doing that? No. Would you be comfortable if a mathematician did that though and said, I can multiply here both sides by t minus 4 like that, and I'm going to split my cases. This is for when t is greater than 4, okay? When t is greater than 4, multiplying by that is multiplying by a positive. So you have 2t plus 7 is greater than or equal to 3 times t minus 4. Or when t is less than 4, but not equal to, because t cannot be equal to 4, okay, so I wouldn't include that, then I have to flip my alligator. 2t plus 7 is less than or equal to 3 times t minus 4. Would this be acceptable? Doing it this way by cases? Yes, this is absolutely acceptable. Do you want to do it this way, which I consider to be the hard way, or do you want to learn the easy way? Let's do the easy way. Okay, I'm showing you this because if someone did this, I want you to understand what they're doing and why. Okay? The reason is when we multiply by something negative, we have to flip our alligator, but because this is an algebraic expression, which can be both positive and negative, we have to now divide into cases. Okay? It's a little bit more complicated, so what would be easier would be doing it this way. If you had to, never mind, I'm just kind of talking now. What would be easier to work with here than a 3? 0. How can you set that to 0? Okay, good. If we subtract 3 from both sides, for what value of t is 3? Wait, no, we can add and subtract from both sides anyway, so I can't fool you there. So we minus 3, we minus 3. Okay, now we get 2t plus 7 over t minus 4 minus 3, and I'm going to multiply that minus 3 by something. What am I going to multiply it by? T minus 4 top and bottom to create a common denominator. And then I say, well, all that whole big fancy thing is now greater than or equal to 0, and now I'm super happy. Now this just falls apart nicely. So let's keep going. We end up with 2t minus 3t, so we end up with minus t, and then 7 minus 12. So that's 7 plus 7 minus 12 all over t minus 4 is greater than or equal to 0. Let's tidy that up just a touch. Minus t plus 19 all over t minus 4 is greater than or equal to 0. Now that's easier to work with. You could also just graph this. You graph 2t plus 7 over t minus 4 and find some value where it actually nicely works out to 3 and solve it by your graph. But I'd encourage you just to do it algebraically this way. Okay, so now we know that t cannot be equal to 4. All right, that makes sense. So there's our vertical asymptote is there at 4. All right, cool. When t is 0, you get 19 over minus 4, so our y-intercept is 19 over 4, but it's a negative number. And our x-intercept, let's set the whole thing to 0. So that would be minus t plus 19 equals 0. So t equals 19. Okay, there's our x-intercept. And we've got our key things that we want to test on our interval table. The 19 and the 4. And our horizontal asymptote here is approaching minus 1. You see minus 1. Minus 1 there. Okay. Note it was at 2 before we did this manipulation, but this was effectively translating it down by 3. So that's why the horizontal asymptote moved down there when we created this new function. Okay, so that shouldn't surprise us too much. So we have y equals minus 1 as our horizontal asymptote. Okay, so a quick sketch of the final situation that we created looks like this. We have this negative crossing over there, so it's like this, like that. And then we're way over here, like this, and that is the point 19, 0. So that's what we're testing. So we already know where this thing is greater than. It's going to be only this range here from there to the asymptote as it goes up to infinity. So let's write it out. We have here our thing that we're going to test. We have the points 4 and 19. If I test t at 20, down here, I have minus 20 plus 19 is minus 1 over 16. So this is minus 1/16, so it's definitely negative in this range. In between here, let's test t at 10, because multiples of 10 are easy to test. Minus 10 plus 19 is 9, and 10 minus 4 is 6. So that's a fancy way of saying 3/2, but that is certainly positive, so we're positive in this range. And then if we test the function at 0, t equals 0. Why did I say t at 20? That's weird. When t equals 0, we have, we already know this, it's where? I have it in my notes. This point, just over there. 19 over minus 4. 19 over 4, but negative. So this is negative over here. So we want this thing to be bigger than 0. So we have our solution is non-inclusive 4, comma, inclusive 19. That's where our solutions are. Okay. Questions about that one? Easy way is pretty easy, right? Yeah, so do it the easy way. It's a lot better than dividing it up into cases. Now this one looks like a little bit meatier, right? So go ahead and crack into this one on your own. I'll pause the video and then we'll take a look at your simplified solution. But before we start, what's your first move here if you're going to do this the easy way? Take this whole thing and subtract it from both sides. Love it. Good. Go ahead and get started on that, and I'll meet you again in just a moment. All right, let's take a look together. So this is what mine looks like. So here you go. I have over here just started by factorizing this expression, which factors into x plus 4 and x minus 5. So I just write that way. That helps me see that this x minus 2 over x plus 4, which I copy down here, only lacks an x minus 5 factor, so I multiply that in. And then this whole thing, we are subtracting it from both sides of the equation, so it shows up there. And I noticed, hey, look at that. What a well-designed problem. This thing only lacks an x plus 4, so we multiply that in. So then I come down, and I have all of it written over the common denominator. That just could be so improved here. There, now I won't struggle to look at it. So here is 1, comes down here, plus the result of expanding and simplifying that. That's that section there. And then the result of expanding and simplifying this is here. But this is where we crucially need to have brackets because the whole thing wants to be subtracted when that comes down. So there it is. It's in brackets. That way when I collect my like terms in the next line, when I collect my like terms in the next line, I have here, so let's go. Yes, so we have here, I have x squared minus x squared, so I collect those first, and then I have minus 7x minus positive 7x. Oh, it'd be so easy to make an error there and have that fall out, be 0, but it's not, it's minus 14x, and then 1 plus 10 is 11, minus positive 12 is actually negative 1. So you'll see that I get that in my next line up there. So this is my fully simplified inequality. And then, and so check that against yours, see if you get the same thing. If not, go ahead and find your error and make an effort to learn from your error. Mine doesn't have any errors today. Okay, we're going to keep going. So I'm just going to copy that down here and investigate our key points. We're interested in x-intercept. So to find my x-intercept, I'm just going to set the numerator to be 0. So that is to say minus 14x minus 1 equals 0. And then I get, well, minus 14x equals 1, and x equals negative 1/14. What a delight. What a delightful number. And then I also am interested in vertical asymptotes. I can see that I have a quadratic on the bottom, which means I can have as many as 2 of these vertical asymptotes. And then an x asymptote, horizontal asymptote that's going to go to 0. All right, so anyway, my vertical asymptotes here are, sorry, what are they? This one and this one. So x is not equal to 4, and x, sorry, yes, negative 4, and x is not equal to 5. So there's my 2 vertical asymptotes. So let's go ahead, and we can also find our y-intercept for fun. So if we set x equal to 0, then we get minus 1 over 4 times minus 5 is minus 20. So we're actually positive there at 1/20. All right, good. And because we're lesser degree over larger degree, our horizontal asymptote is going to go to 0. So that helps inform our sketch as well. So let's take a look. We have now can build this line where we have minus 1/14 and minus 4, so we better put that out a little further. Minus 4 and 5. These are our interesting regions here. We have no holes or anything super strange in this one, so these are the regions that we're going to test. And so if I'm just going to copy out my function again, minus 14x minus 1 over x plus 4 times x minus 5. And I'm just going to test in that with things like f at minus 10. F at minus 10, this gives me an enormously positive number here. And then this is negative and that's negative. So negative times a negative is a positive. So I know my function is positive over here. Okay, I actually get 139 over negative 6 times negative 15, which is positive 90. So 139 over 90. Okay, there, positive. All right. In between, let's test f at minus 2. Okay, so I might write these out, you know, minus 14 times minus 2 minus 1 over minus 2 plus 4 is 2 times minus 2 minus 5 is minus 7. So I can see here this is still positive in this range in here. So this is positive here. Okay, and then we might flip signs here because this is our 0. This is our x-intercept, so in between, let's test f at 0. F at 0 is real easy to test. So we've got minus 1 over minus 20. We already did that. That's 1/20. That's, sorry, minus 1 over minus 20. That's positive again. What? Am I confused somehow? Minus 1 over minus 20. We already knew that was positive. Yes, we already did that. Okay, and then after 5, we're going to have some different behavior here. After 5, we have minus 14 times 5 times, let's test 10. F at 10. Minus 1 over 14 times negative 5. And we can see this is negative here and this is positive here, so we're positive again. And how is this thing positive for all values? So at that point, you might check it against a good graph and just be really like uncertain as to what you've just found. Let's see if we can find any errors. Negative times a negative will be a positive here, and that's very large. This is negative, and that's also negative, so this is clearly positive. Good. Minus 2, let's test this one. We know that there's a vertical asymptote in here, and this is like a x-intercept. That's the value of our x-intercept, so I would expect it to change signs around there and behave differently. And this is another asymptote, so I'm really suspicious that this one might be negative, but it's indeed not. It's positive. So what about this one coming up? And because I can't imagine why this one would bounce here. So minus 2, so you have, this is 28, and that's positive, and this is clearly negative, so that's where my error is. So, as sometimes happens, we get some errors in there. And then you want to always be thinking about the answers that you're getting and saying, wait, this doesn't quite match what I'd expect to be happening. I know that this is my x-intercept right here, and I really expect this thing to come up and change signs around my x-intercept. And indeed it does. So that's what's happening there. It's negative there, and then positive in here for f of 0, and positive over there. So when is this thing greater than 0? I would have... So at this one is precisely 0. So then we can say that negative 14x minus 1 over x plus 4 times x minus 5. This is greater than 0 for the intervals negative infinity to minus 4. Not inclusive because that's one of our vertical asymptotes. So it can't be that. Union with minus 4, no, not minus 4 because we're negative in there. So we have inclusive starting at our intercept between there and 5. So that would look like minus 1/14 all the way to 5. Not inclusive because 5 is a vertical asymptote. And then going off to infinity, we're going towards 0. And as x is very, very large, that's very, very negative. So I feel that this sign wants to be negative. I have two errors in here. Let's test it again. So f at 10, we have minus 140 minus 1, which is negative, over a positive number. So that is indeed negative over here. So it is this final answer, and we make it make sense in that way. Kunal?
Why is the negative 4 included?
Why is the negative 1/14 included? Because that, oh yes, right, because this is, it should not be included. If we changed that one to being like that, then it would be included. But I got hung up on the fact that it was not an asymptote, but an intercept, so therefore include. But you're absolutely correct, because in this case, this one here is greater than, not greater than or equal to. Yeah?
Can we see this in Desmos?
Yes, let's take a look at it in Desmos. So do you want to take a look at this in Desmos or the simplified expression in Desmos?
Oh, I simplified it.
Yeah, cool. Okay, let's go. Okay, so let's go get a Desmos. And we look at minus 14x minus 1 all over. We had x plus 4 multiplied by x minus 5. And the brackets, like so. And we knew that one of the, there.
I think I think it's multiplying 4 by x minus 5.
Yes, you are right. So that's better. Yeah, so it's one of these that has these funky asymptotes. So we have this point there, that's our x-intercept of negative 1/14 there. And past that, it's positive until we get to the asymptote. Our asymptotes were at, if we look at x equals -4 and x equals 5, we'll see our asymptotes there. We're approaching infinity from the negative side, and we're approaching 0 from the negative side there and 0 from the positive side there. And so when this thing was greater than 0, it was up to this asymptote, greater than 0, all the way off to infinity that way, and after the y-intercept, the x-intercept there, all the way towards this asymptote, but not in any other regions. So this range here. I find that like really frustrating to do algebraically, so do it graphically first and then do it algebraically, and you can avoid some frustration. Noticing that I had errors and trying to find them algebraically is like a little bit barf for me, but if your graphing skills are good, just do the graph and then show your algebraic tests, and it's very nice. Again, do the problem 2 different ways and you can avoid errors like I just did. And also thanks to Canal for picking up that I had the wrong sign there. Not greater than, but greater than or equal to. Yeah. Good. So one last example. If we have x units, then our cost is given by this funky function here. So we want to know what production will keep C of x less than $8. Not less than or equal to, but less than $8. So that is to say 8 is greater than this thing over here, which is C of x. 870 plus 2x all over x. So now that I've set this up, I subtract 8 from both sides. I have 0 is greater than 870 plus 2x all over x minus 8. And then I get out my handy dandy, create an common denominator pen, and then I see that I am really, at the end of the day, working with the function 0 is greater than 870 minus 6x all over x. Okay, so now what can I do with that? Any other further simplifications that you would do with this one before carrying on? Yeah.
I will have it like negative 6x minus 870 instead.
Negative 6x plus 870?
Maybe plus.
Yeah, because it's a positive number here.
So you factor it.
Huh?
I was just thinking that you factor
Oh, negative 6. So you're going to factor out a negative 6.
Yeah.
Good. So if we factor out a negative 6, and then we have x minus, so let's actually write it in 2 steps so that those following along can understand what you're doing. 0 is greater than negative 6x plus 870. I would write it in standard form too, so I like that, over x. And then let's factorize. So is that 6 a factor of 870? How can you tell if 870 is divisible by 6? Has to be divisible by 2 and 3. Is that number divisible by 2 and 3? Yeah. So it does divide in evenly. So you divide it out. So you say minus 6 multiplied by x minus 270. So it goes in there 4 times. Remainder 5, did you say? 145? Yeah, 145. That's good. All over x. And now we can find our key points. So We have a vertical asymptote at x is equal to 0. So that's very interesting. We have an x-intercept where minus 6 multiplied by x minus 145 equals 0. And that is to say x is equal to 145 would make that equal to 0. All right, so there's our key point, 145, 0. Okay, and we want this thing to be less than 0. So, and also selling x units, we really already have a restriction on the domain that x is greater than or equal to 0. We're not going to sell negative units. Okay, so we already have that kind of natural limitation on the domain, a practical limitation, not an algebraic one. So we're really only interested in things where x is greater than 0. So a sketch might look like when x is 0, well, if we can factor that out, as x approaches 0 from the negative side, you have, let's start from the positive side, 0.1, just put in 1, very large. So we are very large costs over here, and then we come down, we're going to hit 145 there and go below it that way. So now we set up our interval table. We have 0 there that we can't be. We have 145, and then we have values that are greater than 145 to test. So let's test in here. F is f at 1. You can test f at 1, it's pretty easy. So then you have minus 6 times minus 144. So that's a positive number over there, just large, a positive number over 1, so that's positive. It's positive in here. And we want this thing to be less than, so it changes there. That's where it's exactly equal to 0. And then let's put in f at 245 for fun. 245. So that would give us 100 times minus 6. So 100 times minus 6 is negative 600. Negative 600 divided by 245 is negative. So that's where our costs dip below 8. So we are negative in this range. So then I might say if they produce more than 145 units, their costs will be less than $8. There, the full sentence answer would look something like that. Hey, go for it. So look at it in Desmos for argument's sake. Minus 6x plus 870. Minus 6x plus 870, all divided by x. Doesn't even show up on our graph because it's so high up, but we see that it crosses over here at 145, and as x approaches 0, this thing approaches, their costs approach infinity as they produce towards 0 units. So not being in business is very expensive, although I suppose the negative infinity kind of cancels it out. That's kind of just like practically 0 in this context. But if you just produce 1 unit, it's very expensive. If you produce 2 units, your cost per unit is coming down precipitously. And then your cost per unit sort of irons out a little bit later on. You'll note that this is different than the original expression where we had 870 plus 2x over x. All over x. You know, it looks quite different. But if I say, well, what about I set y is equal to 8, you'll find that this point exactly lines up with that point. Okay? So the 2 points are stacked on top of one another, and we translated the graph down by 8 to make the analysis easier. So that's what you're doing with your inverse operations and why your functions don't exactly match, but they're giving you the same information. Okay. Enjoy. Have fun with that. And any questions, hit me up.